I'm Chris Farmer from West Incorporated, and I'm a senior ecologist here, focused primarily on eagle conservation and eagle behavior. And I just wanted to quickly acknowledge Bob Thresher, who is attending this call. This project started out really from discussions between Bob and myself, and it's his brainchild. And personally, I'm really happy to see where it has gone. I'm joined here by Angela Medina Garcia and Kristen Nasman from West, who are two of our statisticians who will be doing most of the presentation, but I just wanted to tee it up for them. Angela, can you move to the next slide, please? So we've heard a lot about telemetry data thus far and its use in developing the model. It will also have use in validating the model. However, one of the weaknesses with IdentiFlight data, or sorry, with telemetry data, is that although it gives us really good detailed information on the movement of a few individuals, it doesn't give us a really high density of information on the population in general. So we're seeking to use data collected by IdentiFlight to augment that and help with the validation effort here for the models. The advantage we have using top of the world wind farm is that it has a full deployment of IdentiFlight units. And by that, I mean there are 47 IdentiFlight towers at top of the world, covering all the turbines at that facility, and they've been operational for quite some time now. So there's a tremendous amount of data collected regarding eagle movements, completely covering the area that we have our modeling effort focused on within top of the world. We get a lot more individual eagles this way. However, there are some difficulties with the IdentiFlight data, and our role here in this particular aspect of the work is to try and help work through those difficulties and get the IdentiFlight data to the point where it's going to be a useful validation tool for us. The main problem springs from the fact that IdentiFlight is not designed as a data collection system. It is a decision-making system. And so it uses a lot of data, but it also makes decisions based on those data, and it's not really set up with an eye towards making those data useful in a research context, and a lot of manipulation is required to get there. Some of the challenges we need to overcome are figuring out the positional accuracy of identifications of eagles, figuring out the detection probability for eagles for a given unit and their distances from turbines, and also dealing with particularly false positives, because we do not want to validate an eagle model based on movements of things that are not eagles. So now I'm going to hand over to Angela, who will tell you what kind of progress we've been making at kind of digging into some of these challenges. Thanks.
Thank you, Chris. So I'm gonna tell you guys about what I've been doing with this IdentiFlight data. And first, in order to obtain working data set, we selected tracks that were longer, or 30 seconds or longer, because tracks of this duration could give us a good idea of a good representation of actual eagle flying behavior. We also selected tracks that were less than 500 meters above the ground, because this is a representative area where the eagles are mostly at risk. And also tracks that were less than 1,000 meters from the IdentiFlight tower, because this is how far these towers can accurately track eagles. And this filtering resulted in 84,619 tracks of eagle type species from March 14th, 2019 through November 29th, 2020. And here I just want you to be aware that all these tracks can potentially include objects in the air that were not even eagles or birds, or even other species of birds flying. So on the map here on the left, this is the study area, and all the detections by the IdentiFlight units are plotted over the study area. And so yellow here represents the highest count of detections, and the purple represents the lowest count of detections. And here you can see that the detections by the IdentiFlight towers are covering most of the areas around the turbines in our study site. In order to validate our microscale model, we wanted to see how eagles were moving around the towers. And for this, we plotted the distribution of tracks around the towers at the points at which the tracks started and the points at which they ended. So we could see how towers were starting to detect eagles and when they stopped detecting eagles. So here on the left, so see, these are actually density maps for one single tower, an example tower. And on the left, you can see the starting points represented in red. And on the right, the ending points represented in blue. So here you can see that for the most part, the range of detection for both ending and starting and ending points are similar. We also wanted to look at general distribution patterns of the tracks around the IdentiFlight towers. So what we did here was to combine all the data from all the towers and plotted the density. And so here in the Y and X axis, you can see the distance in meters from the center of the towers. And red represents high densities and blue lower densities. So you can see that in general, there is a ring that has intermediate densities. That's a light green area. And that's about like between 300 and 600 meters from the center of the units. So if we look at the distribution of like the distance to the tower on the right, we can see that actually that density of detection is peaking around 450 meters and 600 meters. Next, we wanted to see how the tracks were distributed along the approximate height above the ground. So here in this graph, we have approximate height above the ground on the y-axis and the distance to the tower on the x-axis. And you can see overall here that most of the detections are concentrated in an area between 300 and 700 meters from the center of the tower, and at an approximate height between 25 and 150 meters. And here I'm showing a three-dimensional representation of a subsample with only 30% of the tracks from our working data set. So here again, you can see distance from the tower in both axes. And this time, the color represents the flight height, with purple representing lower flight height values and yellow high values. And I wanted to show you this plot from a different angle. So if you look at it from above, you can see a sort of mosaic of different colors or different flight heights. And that's all over the area of detection of a tower, which is approximately between 100 and 900 meters. So it seems like the towers are detecting eagles at different elevations, independently of how far or how close they were from the tower. Also, the cool thing about this plot is that it can show that even with a sample of 30% of the tracks, you can see the high volume of data that we are working on with this data set. We have also started to look at the overlap between towers because some towers are in close proximity. So two towers, for example, might be detecting the same eagle at the same time. So here you can see two towers represented with the yellow triangles, and the blue represents all the detections by this north tower. And then the red dots represent all those detections that were from both towers and had the same timestamp. So this is telling us that we need to take into account this overlapping area of detection between towers when we estimate the detection probability by the IdentiFlight towers. With this data too, we can assess the accuracy of the locations for the detections for the IdentiFlight units. As next steps, what I show you so far was all the detections by the IdentiFlight towers. So we need to validate our tracks using photos that were taken by the IdentiFlight towers, so we can actually filter out false positives. Our goal is to examine flight trajectories of eagles around turbines, so we can assess potential patterns of avoidance by eagles. And in order to do this, we still need to estimate the detection probabilities and correct the distribution of observations by these probabilities.